In the silent reaches of the cosmos, far beyond what our eyes can see and our minds can easily imagine, lies a world of unimaginable scale. Out there, scattered across the Milky Way, are suns so vast that even our mighty sun, the heart of our solar system, would seem like a mere spark beside them. Among these colossal titans, one reigns supreme: Stephenson 2-18, the largest known star in the observable universe. If you were to stand on a planet orbiting this star, though no such world could survive its heat, the sky would not be filled with light, but engulfed by it. The horizon would glow with a red, burning ocean of gas stretching so far that you couldn't see where the star ended and space began. Every breath would feel like standing at the edge of creation itself, watching matter burn into brilliance. But let's start closer to home. Our sun, though massive by human standards, is rather ordinary on the cosmic scale. It's a G-type main sequence star, roughly 1.4 million kilometers in diameter. It powers life on Earth, holds the planets in its gravitational embrace, and shines with a steady glow that has persisted for billions of years. For us, it's everything. Yet, in the starry hierarchy of the universe, the sun is a modest candle compared to what lurks in the galactic shadows. If Stephenson 2-18 were to replace our sun, its outer atmosphere, the swirling plasma and stellar wind that make up its visible surface, would reach all the way out to the orbit of Saturn. That means Mercury, Venus, Earth, Mars, Jupiter, and even the asteroid belt would be completely swallowed by its burning layers. Our entire solar system would simply dissolve into its fiery body. Stephenson 2-18 resides around 19,000 light-years away, deep in the Scutum constellation, within a massive star cluster known as Stephenson 2. It was first catalogued by the astronomer Charles Bruce Stephenson in 1990. But for decades, its true scale remained hidden, buried beneath dust, distance, and cosmic mystery. Only with recent infrared observations did scientists begin to understand just how enormous it really is. This isn't just a big star. It's beyond comprehension. Astronomers estimate that its radius is 2,150 times that of our sun. Its volume? About 10 billion times larger. Imagine filling a sphere so vast that the sun could fit inside it 10 billion times, and still have space to spare. And yet, Stephenson 2-18 isn't the hottest or the brightest or even the heaviest star out there. It's a red hypergiant, a dying supergiant in its final stages of life. Its outer layers are cooling, expanding, and slowly drifting away into the void. A cosmic heartbeat fading after a long, fiery existence. When we gaze into the night sky, we see stars as distant pinpricks of light, tiny diamonds against the black. But the reality is far stranger. These are not mere dots. They are colossal spheres of plasma, powered by the same nuclear forces that fuel the universe itself. And among them, Stephenson 2-18 is like a god, immense, fading, yet unforgettable. It's hard to imagine something that big. So let's try to picture it another way. If you could travel around its surface at the speed of light, 300,000 kilometers per second, it would still take you over 7 hours to complete one orbit around this single star. 7 hours of pure light-speed travel, just to circle one star. That's how vast this cosmic giant truly is. Yet, despite its incredible size, Stephenson 2-18 is also fragile. The larger a star becomes, the shorter its life. While our sun will live for around 10 billion years, Stephenson 2-18 will likely survive only a few million, a brief, brilliant flash in cosmic time. Its mass burns through fuel so quickly that it's already nearing its inevitable end, a collapse that will one day trigger one of the most powerful explosions in the universe. A supernova, or perhaps even a hypernova. When that day comes, the light from its death will blaze across the galaxy. A flash so bright that if we could see it from Earth, it would outshine every other star in the night sky. And after the explosion fades, all that might remain is a dense, invisible remnant. A black hole, swallowing the light that once made it the greatest of stars. But before that final act, Stephenson 2-18 continues its quiet, burning existence. A distant ember glowing at the edge of human imagination. Somewhere out there, beyond 19,000 years of light and silence, this star still breathes, massive, slow, and dying. It's a reminder of how small we are and how vast the universe remains. Every star is a story, and this one, Stephenson 2-18, is a story about scale, time, and the limits of cosmic endurance. So the next time you look up at the night sky, remember, every flicker of light could hide a world beyond comprehension. And among them, somewhere, burns the largest known star in the universe. A silent, colossal monument to the power and fragility of existence itself. Every star begins with silence. In the vast, cold regions of space, enormous clouds of gas and dust drift endlessly, remnants of dead stars, floating like cosmic ashes. These are the stellar nurseries, the wombs of creation. They are dark, invisible to our eyes, yet they cradle the seeds of new suns. Somewhere, deep inside one of these clouds, gravity begins to whisper. Tiny pockets of hydrogen and helium, the two simplest elements in existence, start to draw together. Slowly at first, then faster. Over thousands, then millions of years, gravity squeezes them tighter and tighter until the pressure becomes unbearable. And then, the first spark ignites. At that moment, the universe gains a new light. A star is born. Most stars form modestly, like our sun, stable, balanced, and destined for a long life. But sometimes, conditions tip the cosmic scale. If the collapsing gas cloud is massive enough, hundreds of times heavier than our sun, it can give birth not to an ordinary star, but to a monster. Stephenson 2-18 is one of those monsters. It was born from a colossal molecular cloud billions of years ago, likely within the dense heart of its cluster, Stephenson 2. That cloud was so immense that the gravitational collapse didn't just form one star, but thousands. A galactic nursery giving rise to a family of giants. Yet even among these siblings, Stephenson 2-18 stood out. Its birth was fueled by an exceptional abundance of matter, collapsing with unstoppable force. When it first ignited, Stephenson 2-18 was not the red hypergiant we see today. It began as a blue supergiant, blazing with incredible intensity. Its core temperature soared to over 30 million degrees Celsius, fusing hydrogen into helium at a pace far beyond comprehension. The energy pouring out from its heart created a furious equilibrium. Gravity pulling inward, radiation pushing outward. This balance, a delicate standoff between collapse and explosion, is what allows a star to exist at all. But the more massive the star, the more violently it burns its fuel. Stephenson 2-18, in its early life, consumed hydrogen at an astonishing rate. In a fraction of cosmic time, its inner core began running out of hydrogen, the very substance that kept it alive. When a star like this runs low on hydrogen, the delicate balance begins to crack. Gravity starts winning. The core contracts, becoming denser and hotter, while the outer layers expand outward. The star grows, swells, and cools, its color shifting from brilliant blue to deep crimson. This is how a supergiant becomes a red hypergiant, a star nearing the end of its life, stretching itself to the very edge of possibility. As Stephenson 2-18 expanded, its surface temperature dropped to just a few thousand degrees, much cooler than our sun's 5,500 degrees Celsius, but its sheer size made it appear far more luminous. Despite its cooler glow, it shines with over 400,000 times the brightness of our sun. The light from this dying star could illuminate the space between worlds, yet the energy behind it is the same force that ensures its destruction. Because the truth is, stars like Stephenson 2-18 are never meant to last. Their brilliance is their curse. As the core contracts and new fusion processes begin, heavier elements are born: carbon, oxygen, silicon, and eventually iron. But each new step shortens the star's life. Unlike hydrogen and helium fusion, which release energy, fusing iron consumes it. And once a star's core is filled with iron, it can no longer produce the power to resist its own gravity. That's when everything begins to fall apart. In its final moments, perhaps only a few 100,000 years from now, Stephenson 2-18 will begin to shudder. Its core will collapse in a fraction of a second. Temperatures will skyrocket to billions of degrees. The resulting explosion will rip through the star's layers, tearing it apart in an instant, a supernova brighter than an entire galaxy. And at its center, where matter has been crushed beyond atomic limits, a black hole may be born. But until that moment, Stephenson 2-18 continues its slow, quiet death. Its surface drifts outward in enormous waves of gas, forming shells of dust that float away like smoke. These glowing clouds, invisible to our eyes but seen clearly through infrared telescopes, are the star's final exhalations. Every breath feeds the future. The carbon, oxygen, and silicon it releases will one day become part of new stars, new planets, and perhaps even life itself. That's the beauty of it. The universe never truly wastes anything. Even the death of a star becomes the foundation for something new. When you look at the night sky, you're not just seeing light, you're seeing the memory of creation. Every atom in your body, every breath you take, every heartbeat, was once part of a star that lived and died billions of years ago. We are, quite literally, made of stardust, born from the ashes of stars like Stephenson 2-18. So when we study the biggest star in the universe, we're not just gazing into space. We're looking into our own origins, the very forge that built us. Out in the quiet darkness, Stephenson 2-18 burns invisibly. To our eyes, it's hidden, veiled behind curtains of interstellar dust that swallow visible light before it ever reaches Earth. If you looked at the spot in the sky where it resides, you wouldn't see anything at all, just emptiness. And yet, behind that darkness lies a star that could engulf our solar system. So how do we even know it exists? How can we measure something so distant, so faint, and so immense that it defies ordinary observation? The answer lies not in the light we see, but in the light we can't. Astronomers use infrared telescopes to pierce the dusty shrouds of space, wavelengths longer than visible light, capable of slipping through interstellar clouds. And in that invisible spectrum, Stephenson 2-18 shines like a beacon. When scientists first studied it through infrared imaging, they expected to find another ordinary red supergiant. But the data told a different story. The star's brightness, its color, and the spectrum of its light didn't match anything known. Calculations suggested something truly extraordinary. A radius over 2,000 times that of the Sun, possibly more. If these numbers were correct, then humanity had just found the largest known star in existence. But astronomy is cautious work. You can't simply point a telescope and measure a star's size directly. It's too far, too massive, and its edges are never sharp. Stars fade gradually into space. So instead, scientists measure luminosity, the total energy output, temperature, and distance, and use these to calculate the radius indirectly. Stephenson 2-18 radiates with about 440,000 times the luminosity of the Sun, yet its surface temperature is only around 3,200 degrees Celsius, incredibly cool for a star. The only way for something that cool to shine so brightly is to be unimaginably huge. So, using these measurements, researchers derived its size, and the result was staggering. If Stephenson 2-18 were placed where our Sun is, its surface would stretch past Saturn's orbit, possibly even approaching Uranus. Think about that for a moment. The warm, golden light that nurtures our world would be replaced by a burning red ocean of plasma, reaching across billions of kilometers. The planets we know would simply disappear inside it. Earth's orbit wouldn't just be close, it would be deep within the star's photosphere. That's how vast Stephenson 2-18 truly is. But even with these careful estimates, measuring a hypergiant isn't easy. The star's outer layers are constantly shifting, pulsating, shedding, and expanding in chaotic waves. Its atmosphere is not solid or stable. It's a boiling storm of gas and radiation. The surface we describe is more like a boundary of brightness, changing from month to month as the star breathes. That's why some measurements list it as 2,150 times the Sun's radius, while others place it closer to 1,500. The truth likely fluctuates somewhere in between, a reminder that even the most advanced instruments struggle to grasp something so extreme. To refine these observations, astronomers turned to radio telescopes. By studying the star's stellar winds, vast outflows of material ejected into space, they could trace how fast the gas was moving and how much mass the star was losing. Stephenson 2-18 is shedding itself at a furious rate, losing the equivalent of Earth's entire mass every few days. Over thousands of years, this relentless shedding creates a halo of dust and gas stretching across light years, the last breath of a dying colossus. Infrared and radio data combined reveal an eerie image, a star no longer crisp or defined, but melting into its surroundings. Its light flickers through veils of its own debris, the ashes of its body, glowing faintly as they drift away. In this sense, Stephenson 2-18 isn't just a star. It's already a ghost of itself, slowly dissolving into the cosmos. Yet even in decay, it holds mysteries. Its exact mass remains uncertain, possibly between 30 and 40 times that of our Sun, though it has likely shed much of it already. It's near the very edge of stellar stability. Any larger, and its outer layers would no longer remain bound by gravity. It would simply rip itself apart. Stephenson 2-18 is a living paradox, so large it can barely exist. Astronomers often describe such stars as stellar extremes, physical boundaries where the laws of nature stretch thin. Studying them isn't just about understanding how big something can get. It's about understanding what the universe allows. How massive can a star become before gravity and radiation tear it apart? How long can something that bright survive before collapsing into darkness? Stephenson 2-18 is the universe's quiet answer to those questions. A natural experiment written in fire and time. Every observation we make, every photon we capture, is a glimpse into a realm of physics that pushes against the limits of comprehension. Through telescopes, we see not just a point of light, but a story, a vast, red, trembling sphere burning itself out to keep existing. And though it lies nearly 19,000 light-years away, the light we see from Stephenson 2-18 today left the star long before humans ever learned to write. That glow, faint and ancient, is a message from a time when early civilizations were only beginning to look up at the night sky and wonder what stars truly were. Now we finally know, and yet the knowing only deepens the mystery. Everything in the universe has a lifetime, even stars that seem eternal. For Stephenson 2-18, the clock has been ticking since the moment it was born. Now, after millions of years of burning with unimaginable power, the giant begins to fade. Deep within its heart, fusion, the process that keeps it alive, is slowing. The hydrogen that once fueled its brilliance has long since vanished, replaced by heavier and heavier elements. Helium became carbon. Carbon became oxygen. Oxygen became silicon. And now, at the very center of this vast, dying sun, the final element is forming iron. It's the last breath of creation, because once a star starts producing iron, the end is inevitable. Iron cannot be fused to release energy. It doesn't give, it only takes. And so, the balance that has held the star together for so long begins to collapse. In an instant, perhaps one day, perhaps 1,000 years from now, the core will reach its limit. Gravity, held at bay for millions of years, will finally win. The entire heart of Stephenson 2-18 will implode, crushing itself to a fraction of its original size in less than a heartbeat. The surrounding layers, unable to fall fast enough, will rebound violently, producing an explosion so vast, so luminous, that it will outshine the entire galaxy. This is the supernova, the most powerful explosion in nature. If we could watch from afar, the light from that single event would blaze brighter than every other star in the Milky Way combined. For a brief moment in cosmic history, Stephenson 2-18 would be the most brilliant object in the night sky. Its light would travel across 19,000 light-years of darkness, carrying with it the final message of a dying giant. But even that brightness would fade. After the explosion, what remains depends on the star's mass. If Stephenson 2-18 is heavy enough, and it likely is, the collapsing core will continue to shrink, compressing until atoms themselves can no longer resist the pull. At that point, the star becomes something entirely different. A black hole, an object so dense that not even light can escape its gravity. Where there was once a massive, glowing titan, there will be only darkness, an invisible well in space, marking the grave of the universe's largest known star. Yet, in that destruction, there is creation. The explosion will scatter the star's elements, Carbon, oxygen, calcium, iron, across the galaxy. These atoms will drift for millions of years, joining other clouds of dust and gas, eventually forming new stars, new planets, and perhaps, somewhere far away, new life. This is how the universe renews itself. Every end feeds another beginning. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was once forged in stars like Stephenson 2-18. You are literally built from the ashes of dead suns. Every heartbeat, every thought, every dream is powered by atoms that were once part of a star that lived, burned, and died billions of years ago. So when we look at Stephenson 2-18, we're not just seeing the biggest star in the universe. We're seeing a reflection of ourselves, the cycle that connects everything. Life and death, light and darkness, creation and decay. It's all part of the same cosmic rhythm. Somewhere, deep in the constellation Scutum, Stephenson 2-18 still breathes. Its fading light drifts through the galaxy, carrying whispers of its ancient fire. And though it will one day vanish, its story will continue, written across the stars, in the dust of planets, and in the atoms of living beings who will never know its name. Because that's what the universe does. Transforms endings into beginnings, turns collapse into creation, turns silence into light. And so, even after Stephenson 2-18 has gone dark, its light will live on, in everything that ever was, and everything that ever will be. As you drift away from this story of fire and silence, take a moment to look up at the night sky. Every tiny spark you see is a reminder of how brief and how beautiful existence can be. If this journey through the cosmos helped you feel a little smaller and somehow more connected, consider joining us here at the Sleepy Minds. There are endless stories like this one waiting to be told, quiet wonders hiding in the dark. So take a deep breath, close your eyes, and if you'd like to keep exploring the universe with me, one calm night at a time, don't forget to like, subscribe, and let the stars keep you company. Until next time, sleep well and dream of the infinite.